Hi everyone, welcome to the talk on neural networks. So before we get into it, I just wanted to explain why I wanted to do this talk, and the whole idea is to give developers or people in the tech industry an idea of actually what's happening under the hood when working with neural networks. When you try to learn it yourself, usually you're bombarded with a lot of math and a lot of complicated equations, and this is our hope to demystify that with this talk. So a little bit about me. I'm actually from South Africa, so I flew all the way like 27 hours to get here. I work for a company called Intellect. We do custom software engineering. And funny enough, we actually have a presence in Sydney in the next month. But we're originally a South African company. So I've worked in a whole range of industries from finance to agriculture, health, gaming, all sorts of things. Building a lot of web applications, backend integrations, and a lot of data management as well. I'm also, shameless punt, I'm writing a book with Manning, grokking AI algorithms that should be out early next year. Also run the AI ZA, so ZA is short for South Africa, run the AI ZA meetups. They happen monthly, where we try and help developers and people in the tech industry get to grips with what really is AI and how they can apply it to their work. And yeah, I like traveling and hiking and drinking sometimes. But yeah, enough about me. So when we think about artificial intelligence, I think first we need to talk about what we believe intelligence is. And as humans, we base our understanding on ourselves, right? So if we look at Stephen Hawking, he focuses on the ability to adapt. He believes intelligence means you're able to adapt to different environments as they change. Salvador Dali, he focuses on ambition. So he says for someone or something to be intelligent, it should have ambition. What's ambition? It means you have some goal and some internal goal that you've created, and you try to change your behavior and change what you do to achieve that goal. Einstein focuses on imagination. So he believes intelligence means you should be able to imagine new things, invent new things, and a lot of creativity is involved in that. Now, given these three different schools of thought, and there's far more than that, we can conclude that we're basing our understanding of what intelligence is on who we are as humans. Right? We believe we're the most dominant species and we're the most intelligent species, so we're the benchmark for intelligence. But we observe intelligence all around us. So a single ant, if you look at a little ant, do you think that's intelligent? Probably not. But in a colony, these ants can do really intelligent things. So what ants do is they drop little pheromones, and they're just perfumes. And they use these perfumes to communicate with other ants. And through 10 to 20 different pheromones, these ants can recruit other ants to help them. They can show recognition to other ants for something they've done. They can ask for another ant to groom them. And this is a lot of things that us as humans do. We just communicate it verbally. And you'll see these ant colonies are able to build these huge communities around the world while working together. So in isolation, they're pretty dumb, but together they have this really smart emergent behavior. Now, ants are organic and so are humans. And we're trying to make computers intelligent. So if we had to compare our hardware, what kind of specs do we have to a computer? What would that be like? CPU. So in each and every one of you right now, you've got a CPU processing power of 1 exaflop. What's an exaflop? It's a billion operations per second. That's 100,000, a million times faster than the best supercomputer that we have right now. If we look at RAM, it scales to 2.5 petabytes. That's because of the complex connections within our brains. That's about 210,000 DVDs. Right? And then if we consider our DNA as hard storage, like a hard drive, it's 150 zettabytes, so plus minus 256 billion DVDs. So this spec is in each and every one of you. And yes, we're really intelligent, and this is why. We're a really powerful organic computer. So there's a lot of fear that computers will rise up, like in the Terminator, and destroy us all. But I think before they do that, they're going to need to kind of get to the spec of computing. And that's why there's a lot of research going into quantum computing, which would solve some of these problems in achieving that. So when we think about artificial intelligence, we see things like fraud detection in our banks, or intelligent things like Cloudflare. They do like really good routing and smart routing. They know when you're being DDoS'd. Those are examples of narrow intelligence. These are applications of learning and making something smart that makes the relevant decisions in a specific context. So if you take that fraud detection model and ask it to make you some toast, it's not going to understand that. Whereas humans, we're at general intelligence. So when you were a child, if you touched something that was really hot and got burned, next time you kind of feel something is warm, you're gonna be a bit wary, even though it's something different, right? You're able to generalize and transfer the learning from one context to another. And then there's superintelligence, which is something that an artificial general intelligence could become, but we really don't know what that is. And even if it happened, would we even understand it? I think that's more of a philosophical debate. So let's focus on narrow intelligence. Out of interest, we can measure intelligence in a computer like we measure humans. There's something called a G factor, general factor, basically tests how general your problem solving and reasoning and cognitive abilities are. An IQ test is an example of a G factor measurement. And this isn't just done on humans. We do it with apes, we do it with rats, we do it all sorts of things. So potentially we could develop something like this that could test the general intelligence of a artificial intelligence. All right, so how does this all fit together? If we've got this realm of artificial intelligence, we also talk about machine learning. So machine learning is a discipline within AI. And then you might have heard of deep learning, which is an even more specific discipline within machine learning. And neural networks is used throughout these different spheres of AI in different ways. So let's focus on machine learning for a bit. What exactly is machine learning? Well, if we went to a store and we bought some apples and oranges, we bought 20 apples and 20 oranges, and we measured how smooth each fruit was and the weight of each fruit. And if we laid that out on a chart, we might find something like this, where perhaps if something is more smooth and heavier, it might be an apple. Maybe it's more rough and weighs less, it's an orange. And what we want to find with machine learning at its simplest form when we're trying to find patterns is to distinguish these two different categories. So we're really trying to find this line in between those two categories. And if we look at this, we could solve this pretty easily. If we had this on a piece of paper, we could easily find that line. We could even, with some trivial math, find what that function is. But what happens when your data looks like this, and that function's a little bit more tricky? We'd probably still be able to do it. Becomes a little bit more difficult if your data looks a bit different. And what if we consider not just smoothness and weight, but also diameter of the fruit? And we're working with a three-dimensional space. I don't think any of us would be able to compute that on a piece of paper offhand, just off the bat right now. Now, that's what we're trying to do with machine learning. We're trying to figure out what these functions are that describe the different categories in our data. All right. So briefly, steps in machine learning, probably the most important step is collecting and understanding your data. You need to collect a whole bunch of data, you need to understand the context that data is in. So if you're working with fraud detection, you need to really understand the financial data you're working with. Right? You need to prepare your data. So in the real world, data is ugly. I'm sure a lot of you have worked with a lot of data in your careers. And you expect it to be perfect if you look at an entity diagram or something like that. When you look at the data, there's missing values. There might be something that says Sydney, spelt out completely, and then the next one says SYD, or whatever it might be. But you know as a human, both of those mean Sydney, but a computer doesn't. So a lot of data preparation needs to happen before this data can actually be usable. The next step is training a model, and neural networks is one way to train that model. And that's what we're going to be focusing on today. After that, you need to evaluate that model. So you've trained a model, and it's pretty good at describing what's apples and oranges, but you need to decide if it meets your criteria, and you need to set a criteria. If it's able to describe what an apple or orange is at 95% accuracy, are you happy with that or not? And if you're not, you need to improve the performance. And this is going to happen most of the time. You're likely not going to be happy with the first result you get. And you got to go back and iterate. So this may mean collecting more data or figuring out or getting a deeper understanding of that data. It may mean preparing your data differently. It may mean not using a neural network. Maybe you have to use something different to solve this problem. And then you have to evaluate again and then probably improve until you're happy. So let's focus on training a model. How could we do that? So here's a list of common machine learning techniques, and these aren't anything new. These have been around for decades, right? This boils down to statistics. Today we're going to be talking about neural nets. So let's look at the history of neural nets. The first model of a neuron was actually defined in 1943, right? So it's nothing new in 2018. In 1951, a researcher by the name of Minsky defined the first artificial neural network. In 1958, researcher Rosenblatt introduced something called a perceptron, and he really believed that he solved the problem, the AI problem, with the perceptron. And we're going to look at what a perceptron is in a bit. In 1969, Minsky proved that the perceptron could not solve AI because it couldn't solve nonlinear problems. So remember that diagram that we saw with the two parabolas? That wouldn't work with the perceptron. And unfortunately, Rosenblatt actually died in a freak boating accident. So he couldn't work on his idea for a perceptron any longer, and he couldn't refute these claims. In the 80s, this was unrelated to computer science, but researcher James worked on a paper trying to describe the workings of the human brain and how it operates. I remember what we're trying to do with a neuron or a perceptron is apply how our brains work into a computer, into an algorithm. And then in the 80s, a bunch of researchers created this concept called backpropagation, which we're also going to look at. And they used the idea of a perceptron, and they used backpropagation to enhance it and make it applicable to solving more problems than it originally could. And it took them quite a while, because only in 2006, that same group of researchers released some really cool findings where they used tips and tricks with just the perceptron and backpropagation and tweaking the algorithm and the parameters of it to do some really cool things. And you might have seen those ghostly looking faces where we did edge detection that came out in 2006. That was a result of the perceptron using backpropagation with these tricks that they've been playing with all these years. So why today? Why has this become so popular today if it's so old? And in my opinion, it's for three reasons. Abundance of data. So with the boom of the internet, we've collected so much data. And with better computing performance, we're able to process that data. Now, these statistical techniques have been around for decades, and we haven't really been able to apply them properly because we couldn't compute it and we didn't have the data. Now we do. So for example, this little USB stick here, I've got a demo to show you. This thing can process neural networks 5 times faster than my MacBook, right? And this thing fits in my pocket and costs $70, right? So that's a testament to better computing performance. This is really accessible to most people right now. I think most importantly, there's business opportunity. We wouldn't be doing things if businesses couldn't benefit from it. And with AI and machine learning, businesses can make better decisions or even offer products that they couldn't imagine themselves. Okay. So let's look at this whole idea of a perceptron and a neuron. So this is a single neuron, and we have billions of these in our brains. They consist of something called dendrites. These things receive electrical signals from other neurons. And this is also connected to your nervous system. So if you pinch yourself, these dendrites are receiving a signal, and they're passing it on very quickly to its cell body, which decides how much of that signal must I pass through to the axon which then passes it on to other dendrites of other neurons through the synapses. So essentially, it's just all these links of neurons, interconnected neurons, that are passing through electrical signals that decide in isolation how much of that signal they should pass through. Right? So the signal goes through to the nucleus. It decides how strong should my output be. It goes down the axon, eventually gets sent through the synapses, which also applies some sort of threshold as to how much of that signal it passes through to other dendrites. So in other pictures you may have seen, these neurons look like they're connected physically. They're not. There's small spaces between the synapses and other dendrites, and that's why there's some loss in signal or change in signal between them. All right. So how would we represent this in a model that we could use in a computer or in a programming language? This is a perceptron. So you'll notice we have a bunch of inputs, which are our dendrites. If you recall the previous slide, we've got our weights, which is essentially the synapses, what's being applied by the synapses. We've got our cell body, and then we've got an output, right? So we're taking in some inputs, and just to clarify some of the mathematical denotations, inputs are defined by X, weights are always W, and your outputs are Y, right? So the first thing that your perceptron is going to do is it's going to sum all the inputs. It's going to take X, multiply it by the weight, add that to X1 multiplied by W1, etc. So we put some numbers into this. Let's see what would happen. We're firstly going to take 0.15 multiplied by 0.22, get a result, and then do the same for all the inputs that's coming into this perceptron. And eventually we're going to get this number 0.683, right? Then we've got something called an activation function, and traditionally in the perceptron, the activation function was a step function, which is quite simple. It says that if the sum is positive, then return 1. If it's not positive, return 0. Right? So in this case, it is positive, you're going to get a 1, and your output would be a 1. And that's essentially how perceptron worked. And Rosenblatt really believed that this could solve AI. And all this is doing is it's taking in some inputs, applying some weights to them, applying some function that decides how strong of an output do I give, given these inputs, and in this case we get 1. Right, so if you had to write this in code, this is just an example in Python. It's pretty simple. We're going to get an input layer with a whole bunch of input values. We've got our weights described in another array. We're going to multiply each input by the weight. We're going to sum them, and then we're going to apply the activation function. In this case, I'm using a really cool library called NumPy, and it's got a built-in function for the step function called Heaviside. All right, so we can code a perceptron really simply, right? And what that's going to be able to do is it's going to be able to figure out this line. Okay, if we're working with a linear problem, it's going to be able to figure out what's this line between our two categories. In our example, is apples and oranges. So again, the step or threshold function, that's what it looks like. You'll see it's very strict. If something's negative, it's always going to be 0. If it's positive, it's always going to be 1. Right? There's no leniency in this activation function. Another popular one that's used is called the sigmoid function, and you'll see what this gives us is a smoother value between 0 and 1. So if we have a negative value, we might get something that's closer to 0 but not 0, which still makes it useful to us. And then you get other activation functions that you might want to use in different contexts. So this is an example of a hyperbolic tangent. You can see it's very similar to the sigmoid function, but this one goes from -1 to +1. Right. So now that we understand how a perceptron works, how would we apply this to using a trained neural network? So let's just assume that we had a neural network, we trained it, It knows what it's doing. It knows how to classify something. How does that actually work? So let's take this data into account. Please excuse the miles per hour. I did this talk in the US, and I think they would have gotten confused with kilometers. So we'll get miles, right? So in this case, we've got a data set with current speed, terrain quality, degree of vision, total distance traveled. So let's assume this is a self-driving car, even a human driving a car, and we've managed to collect this data. And we're saying, in this case, when someone was doing 40 miles an hour, with half-decent terrain quality and half-decent degree of vision, and 50,000 miles of driving experience, when it encountered an object that just appeared in front of the car, it didn't collide. I'm going to say 0, it didn't collide. In the next one, it was driving at 70 miles per hour. So that's about 120 kilometers an hour. It was driving on very poor terrain quality, with very poor degree of vision, but it has a lot of experience driving. But given the same circumstance, it did collide. Now, I specifically made this very obvious. If we eyeball this, we can easily see this person was driving way too quickly on poor quality roads. Right? It's obvious that they would crash. What we're trying to do with this neural network is, given hundreds of thousands or millions of records of this, we're trying to make it find the relationships in the data that may not be obvious to us. So in this case, it is obvious. But what we want the network to do is find all of these unobvious relationships in the data that can determine what factors contribute to a collision or not. Okay. See, in that one, the person's driving very slow, so I guess an accident isn't very likely. Now, before we start doing anything, we need to be able to standardize and scale our data. So we have a good understanding of what miles is, of what kilometers are, of what degrees mean. A computer doesn't. So we need to be able to scale this to a standard scale that a computer would be able to understand. And usually what we do is we scale it to values between 0 and 1, or values between -1 and 1. So how would we do that with this data set that we have? Firstly, we need to find, we're gonna use min-max scaling. So firstly, we want to figure out what is our minimum and what is our maximum for each of these features. So for the feature of current speed, we know that you can't go slower than 0. And we're going to assume that you're never going to exceed the speed limit. We're going to say the maximum will always be 70. With terrain quality, we can see we have a rating between 0 and 10. With degree of vision, we're going to assume you only can have a maximum of 360 degrees field of vision, unless you're working in like a 3D space. But let's not get too complex. And then for total distance traveled, 0 is obvious. You've never driven before. But I've decided if you've got more than 300,000 miles of driving experience, we don't care if you have more than that. We're going to consider you a decent, experienced driver. And that's a decision I've made as a human now in a lot of these instances. So when we created this data set, we've made a scale of 0 to 10. And here I'm making an assumption that if you have more experience than that, it doesn't matter. And here I'm saying, okay, no one's ever going to disobey the road law, all right? So if we take that into account, how would we start scaling this? We use simple min-max scaling. That's a simple equation for it. You take your inputs minus the minimum and divide that by the maximum minus the minimum. So in the case of current speed, where the minimum is 0 and the maximum is 70, we're simply going to apply 40 miles per hour minus 0, which is our minimum, and divide that by 70 minus 0, which is our maximum minus minimum. And we get 0.57. It's a nice value between 0 and 1. And we're going to do the same thing for every other feature, right? And you see we come out with a nice data set that's normalized and standardized to a value between 0 and 1 that a computer can understand. Again, if you wanted to code that, you could, but there's a lot of libraries that can help you with that as well. So we get this. Our data starts looking a bit more standardized and usable. We assume that a computer would be able to understand this a lot easier than it would miles and degrees of vision that we had in our original data. All right, so now let's start building our neural network. We know that we have 4 features. We've got our current speed, terrain quality, degree of vision, and total distance traveled. So for our inputs to our neural network, we'll choose those features. That means we're going to have 4 input neurons, right? Then we're going to choose some amount of hidden neurons. So I randomly chose 5 neurons here for this example. These are essentially going to be your perceptrons. Each of these is its own little perceptron that's working in this hidden layer. And then we have weights between every input neuron and every hidden neuron. In the case of a perceptron, it was quite simple. There were connections from every input going into a single neuron. And here we have the exact same thing. Just because there's way more many lines, it doesn't mean, well, it does add to the complexity, but it's from a conceptual level, it's the same thing as our perceptrons. And then obviously we want an output to indicate, are we likely to crash or not? All right? So you've got your input nodes, you've got your weights between your input nodes and your hidden nodes, and you've got your output nodes. Now, if perhaps we had more data and we wanted to do something different, like we wanted to determine how likely is it that a crash will occur and how severe the crash would be, we could have 2 output nodes, right? But for the sake of simplicity, let's stick with 1. Now let's try to figure out what each of these little neurons are trying to do. Perhaps this neuron right here is concerning itself with what's the relationship between terrain quality and degree of vision when crashes occur. Is there some sort of relationship there? Every time someone crashes, is there something about the terrain they're driving on and how much that person could see or how much that car could see? Maybe this neuron is concerned with the terrain quality and total distance traveled. When crashes occur, do people have maybe less distance traveled on that terrain quality? Or maybe the neuron's considering itself with how fast you're going on the terrain you're driving on and how likely of a contributor that is to you crashing. So intuitively, these neurons are working together, much like the ants were working together, to give you this emergent intelligence, whereas in isolation they were quite trivial. They only solved linear problems, like the perceptron did. So again, from a mathematical perspective, we denote the inputs as x, the hidden units, now, this is a new one, as h, and the output is y. And maybe it starts looking like this. Maybe our weights aren't that strong between certain neurons. Much like we just looked at, maybe some neurons don't care about certain features in your data set. So your weights might be 0 or something very close to 0 that don't really impact the summation and the activation function that happens in it. So you've got all your weights here. I'm not cancelling out those weights completely. They still exist. They just might not be a big factor in this network. And then sometimes you have something called a weight bias. And also, as a human that's configuring this network, we might introduce a weight bias to change the way the neural network makes decisions. All right. After evaluating it, we might see that things tend to fall to one side and we want to bias everything. There's no harm in biasing everything because you're impacting all the weights. If you were impacting specific weights, then you're messing with how this network is gonna function. All right. So if we put some numbers in here, so this is that first row that we put in.
Sorry, one question. So the data is hard and easy to understand, but the weights, is that something that we choose as we model this, or is the AI figuring out what the weights are?
So I will get to that when I talk about training it. So remember, we're talking about using a network. The weights have already been trained, so that's magic. The weights are there, and you're using this network, all right? So let's work on that premise for now. We're using this network. These weights have been trained. We feed in a specific row of data. It's going to do what we did with the perceptron. It's going to sum that input and that input with their respective weights using that formula, just like the perceptron. And we're going to, this time, use a sigmoid function on that, right? We get a value of 0.5 2.5041. Okay? And we're going to do that for all of our hidden neurons. And then we get this output, 2.5174. What's that telling us? It's not telling us much. Because what we need to do on our output node is also apply the sigmoid function, and then suddenly we get 0.9253. Who can guess what that might mean? Yeah, so it's a 92.53 probability that a crash will occur. Okay? So by using the magic and putting in our input, it's given us something meaningful. It's predicted that a crash is going to happen. All right? And now this is where I just want to get a little bit into the math, because when you're trying to learn this stuff online or through courses, you can get quite caught up in the math and maybe scared to pursue it further. But let's look at what it might mean. So firstly, we need to understand a few data types. We've got scalars, which are just numbers. Then we've got vectors, which are arrays. And then we've got matrices. They're also known as second-order tensors. Essentially, they're two-dimensional arrays, or arrays within arrays. Then we get something called a tensor, which is essentially a data structure that encapsulates scalars, other vectors, other tensors. And what's interesting is we can visualize that. We could make a dot somewhere, and we can see it's 22. We could make an array, and we could visualize that on a plane. We could make a 2D matrix and visualize that on a graph. But a tensor becomes something very difficult for humans to imagine, because we live only in a 3D world, right? And you might have heard of a library called Tensorflow. It was built by Google, and this is essentially what it does. It's really great at computing tensors, right? So the key thing to understand here is you have your scalars, which are very simple, and your tensors, which become very complex and hard for humans to understand. Now, if we had to look at our neural network again, we've got our 4 inputs, which is essentially a vector, right? x0 to xn. In our case, it'll be x0 to x3. Then we have all our weights between our inputs and our hidden nodes. That's what it would look like, because we've got a weight for each input going to each hidden node. It's essentially going to be a second-order tensor, or a matrix. All right? We spoke about that bias, so let's include it in our equation for now. We're going to have a bias for our weights. And then we have our activation function that's applied to each and every line here. All right? That will eventually give us our output. So if we had to represent that, it would look something like this. Our output's equal to the activation function of each weight times each input, and summing them, right? And if we had to simplify that, that's what it would look like. So when you see these functions when looking at neural networks, that's essentially what it means. It's trying to represent that visual graph as a function, because it is just a function. Okay, so now we get to, it will address that question. What happens when we're training a neural network? Now that we know how to use one, how would we train one? And what we need to train is those weights, right? We knew that we provided with input. We know that it was summing the inputs with the weights. We know it was applying an activation function. But what is the actual learning? And the learning comes down to those weights. So if we go back to our perceptron, let's introduce something. It's called a cost function. So now, switch it completely. We're not using the network, we're training the network. So we're using data that we know. It's labeled data. So what labeled data is data that you saw at the beginning. We know, given these conditions, a crash did occur or crash didn't occur. Okay. So we know how well this network is going to learn. So what we're going to do is we're going to put in the inputs, and we're going to randomly initialize these weights. And a common approach is to randomly initialize the weights to something close to 0, but not 0. All right? We're still going to do the summation. We're still going to apply an activation function. But this time, we're going to get something called y hat. We're not going to get a prediction. We're going to get a trained prediction. And we're going to have to tell it how wrong it was. So we get a result. Let's put some numbers in here. So we've got these inputs coming in. We've got these randomly initialized weights. We get our sum, we get our activation function, and we get this value 0.664. But we know that a crash occurred. So we know that it's 1. So we need to calculate the cost of that. And how we do that is we take y hat, which is the result that it computed, subtract that by the result that it should have been, squared. Now this 0.5 is a constant, and what that value means is your learning rate. Okay, so you can adjust that, and you need to determine that as you're creating your model or creating your network, and figure out what's the optimal learning rate to give you the accuracy that you're looking for. So in this case, we're just using 0.5, and this also, again, has no impact to, it's not biasing your network in any way, or not biasing any specific nodes because it's applied to your entire network. So given that, we get a result of 0.056. And we now need to feed that back into the network, and the only thing that this network has control of are its weights. And this thing is telling the network, listen, you were a little bit wrong about that prediction, and this is how wrong you were. Go fix something. And what it needs to do then is adapt and adjust these weights to fit what its error rate was. Right? So if we give our bigger network again, and we do the exact same thing, we want to push that cost to all of the weights in our network. So just like the Perceptron pushed it to all its weights, even though we have different weightings between different inputs and hidden nodes here, we need to push it to every single weight on the network. Right? And this is done per record. So this is our label data. We know that this one didn't crash, this one did crash. We're going to do this for every record, and it's going to constantly update its weights and learn, right? Because we're telling it how wrong it was, it's adapting to how wrong it was and improving. And it's done for each record until we get a desired accuracy. Okay, so that's pushed through there. How do we calculate these weights? So now we know how wrong the network was, and we know that there was some randomly initialized weight that's now changing and adapting as we tell it how wrong it was for each record. How do we calculate that? Now, in our simple network, it might be easy. So maybe we can even try permutations of different numbers and see what gives us the best accuracy, right? Like brute force it. But even in a slightly bigger network, which isn't really that big, where we have 56 different weights, it would take millions of years, literally millions of years, to compute that. Right? So we need to find clever ways to help us adjust these weights. And that's where a little bit of calculus comes into play. So if we had to graph for a specific weight, we're looking at one specific weight now, and we're saying when it is closer to 0.5, that's actually where we have the lowest error rate. And we don't know this offhand. This is in the mathematical universe for that specific weight. The most optimal weight is something close to 0.5. How do we find that? Calculus comes in, so gradient descent. You might remember gradient descent from high school. Essentially what it says is you calculate the slope at that point, and if it's a negative slope, you know that you need to move right. And if it's a positive slope, you know that you need to move left. And what ends up happening is something like this. So in this trivial example, after about 4 hops, it's found its minimum. Okay, we're never going to get an error rate better than that, so that weight should be 0.5 in this case. But what happens if the function looks like this? Remember, nothing is perfect. We always have problems to deal with. Your function might look like this, and your weight gets initialized there. Okay, you can see why I said you should initialize your weights to something close to 0 but not 0, right? So what if it gets initialized there? If we use typical gradient descent, we have the risk of falling into that local minima and never getting to our global minima. And that's where you can use a trick with gradient descent called stochastic gradient descent, which is the variation. Right? So now you can see how matrix manipulation has a role in neural networks and how calculus has a role in neural networks. So when you're calculating these weights, it's as simple as taking the weight that it was initialized with, or its current weight, and you add the negative of the slope of the cost function. So if we put some numbers in there and we had 0.23, and we calculated the negative slope to be 0.18, if we add that, we get 0.05. So for that record, we've now adjusted our weight, and we'll do that for every weight in our network. Right? So again, you calculated the cost, it gets pushed to every single weight, and that calculation you just saw applies to every weight in the network. And through thousands and thousands of iterations of teaching it, given these values, this is what happens. Those weights get adjusted almost perfectly to give you really accurate predictions. So what we've seen is an example of supervised learning, where we've got data that's labeled. We know, given a data, what's the outcome. There's also unsupervised learning. And this is useful in finding the question you want to ask. In our case, we knew the question. We're asking, will this collide? Sometimes you don't have a question to ask. You just have a lot of data, and you want to find a question to ask. And that's where you use unsupervised learning to find hidden structures in this data and reveal them to you. So as a human, you find these structures, and then you think of questions to ask this. You try to label the data to help you with your supervised learning. And then you get reinforcement learning, which also uses neural networks in some aspects of it. But this is really inspired by behavioral psychology, much like how we learn. As I said, when you were growing up, if you felt something hot, you were not rewarded for it. You were penalized for touching it. But if you did well in your homework, you sometimes got rewarded. So you did more homework, maybe. And that's how reinforcement learning works. So when we look at designing a network, here's an example of one that's a bit larger. We concern ourselves with our inputs and our features. So gathering that data and understanding that data is really important. We also need to decide how we're going to normalize the input data. All right. We need to decide how many output nodes do we have? What are the questions we're asking? So in this case, maybe we are asking, will it collide? What's the chances it will collide? And what's the damage? We need to decide on the number of hidden layers in our network. There's a cool tool, online tool by Google. It's called Tensorflow Playground, which gives you a good understanding, or helps build an understanding of how you decide on how many layers to have, how you decide on how many neurons to have in every layer. All right. Your weight initialization scheme, that's also something you need to decide on, and something you can configure. Activation functions, use a sigmoid function, hyperbolic tangent function, and this is very dependent on the input data you're working with and the layers you have in this network that you're designing. Then your cost function, how you're going to calculate cost. And with that, what's your learning rate going to be? Right? Now, given all of these things, you can see that you have quite a lot of control of the neural network, and you need to configure all of these different variables, and different configurations will give you different results. And this is why humans are really important in designing these AIs. So some people think, oh, if we design a really good neural net, it can design other neural nets. And they're somewhat true. I'm going to go through the tools in a bit, and there are some really good tools that you can use where you don't need to really understand the nitty-gritty of how it works. All right, lastly is the stopping condition. So when do you stop learning? Do you stop when a certain accuracy has been reached? Do you stop given a certain data set you have? You only have a certain amount of data, so you're going to stop there. You need to decide how you stop learning. So when you want to get into this, the most popular tech to use at the moment is Python, because a lot of libraries support Python related to neural networks. NumPy, you saw an example of it. It's really good at helping you with matrix manipulation. And you can see there's a lot of matrix manipulation that happens with neural networks. SciPy, not necessarily specifically for neural nets, but great for interpolation, linear algebra. It helps you perhaps prepare your data. and scale your data. Pandas, it's a really good tool for manipulating your data and creating data frames. So in that whole preparation step, pandas can help you out quite a bit. And then being humans, we want to visualize things. You don't just want to see these numbers. We want to see perhaps what it looks like on a graph. So we can ourselves maybe try and gain some intuition of what the data means. And matplotlib is a great library for that. Now, if you don't care for the math or anything, go and use scikit-learn. Like with 2 lines of code, you can build a neural net or decision tree and already have something really smart if you have simple enough data. So scikit-learn is really great. And then TensorFlow, we spoke about TensorFlow. It's essentially for numerical computation. And TensorFlow, you might think it's just for neural networks, but it's actually useful in other contexts. Any context that has graphs that require computation, TensorFlow is really powerful. And then Keras. Keras is, again, for lazy people like me. I don't want to go and build this whole neural net with TensorFlow and code each node in my network and how it's linking to other nodes. With Keras, you can simply describe a neural network in a few lines of code. You can say that you want X many input nodes, Y many hidden nodes, however many layers, and it will design the neural network, and it works with TensorFlow and a whole bunch of other computation engines as well. And if you're a Docker person, all of this stuff is available in a Docker repo called Depot, which you could find as well. So if we just want to gain some intuition as to how this stuff fits together, Python is our base programming language. NumPy is helping us with all our matrix manipulation. SciPy, Pandas, and Matplotlib are helper libraries that we can use. And then we can use scikit-learn for some more basic machine learning algorithms, or TensorFlow and Keras. This might be a bit biased because I like Keras and TensorFlow. There are other options out there. PyTorch by Facebook is another option. And I'd also recommend Notebooks. Notebooks is a way to code Python code in your browser. Obviously, it's going to run on a server, but it's really great for learning. You can write notes, and it'll show you graphs and things like that. Right, so just to look at some other neural networks, a recurrent neural network. You might have heard of this. What this is essentially a neural network that has a concept of memory. So if you wanted to, in a simplest form, it's the same neural network copy-pasted a whole bunch of times. And when changes happen on the one side, those changes are propagated to all the historical neural networks. But much like our memory, it's applied less. So if an event happens to you now, and it's pretty traumatic, it might change your memories from more recently, maybe a week ago, but it's unlikely to affect memories from your childhood. And that's how this neural network works, essentially. And this is great for figuring out speech recognition, handwriting recognition, even composing music. And then something you might have heard of is a convolutional neural network, which is used to, it's a special type of neural network because it's really designed to work with imagery. And essentially what it tries to do is find relationships in images. So maybe there's a relationship between a bumper and a wheel, and through learning through all of these images of cars, it realizes, okay, given these certain artifacts in an image, I know it's a car, right, at its simplest form. So let's have a look at some code. Right. So let's look at just this class here. It's a simple image classifier, and why I want to show you this is to show you how simple it is to get started with machine learning and even deep learning. So this example is using some deep learning, and it's going to be using this cool little device to train the neural network and process the neural network. So if we look at some of the methods here, we've got open device, that's going to open this thing. Sorry. Is that better? Yeah, thank you. Cool. So what we have here is open device, and again, I'm very lazy. A lot of smarter people have trained neural networks to do image classification already. Why would I want to do it? I don't even have a lot of images, just have a bunch of selfies. So what we're going to use in this example is we're going to load a model. We're going to find a model that's already trained, and we're going to use that model. We might need to pre-process the image that we are trying to classify. So in some cases, the graph might only work with certain sized images. Maybe it requires square images, right? Maybe it requires different formats. So older color modes, BGR, was an old color mode that kind of stuck around. Its legacy stuck around. So you might need to convert it from RGB to BGR if that specific graph was developed to work with BGR, right? And then I'm going to infer the image. I want to figure out what does this network think this image is. Print some results, and there's a whole bunch of helper functions here which are just to help with command line, to help us with our inputs, right? So in just, 100 lines of code or so, we're using this device, and if you weren't using it, you'd probably write 50 lines of code, and you've got some image classification working. So in this case, we're using Google's ImageNet. That's essentially the image recognition model that's used on Google Images and was trained using Google Images. And I was able to get that model. It's available for free. I was able to get that and use it on my computer, right? So you could easily use this in your projects. So let's see what we have here. Let me just make sure it found the drive. All right, so it's found the neural compute stick. Everyone likes cats, so let's do. Oh, I named it something else, so you don't think I'm cheating. I named it owl. So all I'm doing is I'm calling that Python file. Can you guys see the command line here? Better? Cool. So this is the cat, and I called it owl because it could be an owl. And what it's done here is it's said that it's 50% sure that it's a Persian cat and 5% sure it's a kite, which isn't unreasonable. What we could do is we could also here just determine how many predictions we want. So if we want 4 predictions, let's run that again. Okay, Persian cat, kite, lynx, weasel. It's 2.8% sure it's a weasel, right? Now what's really impressive is this took 95 milliseconds. Okay, and I'm running an Ubuntu VM on Mac OS. This VM has 2 gigs of RAM. That's why you can see my command line and everything's grinding to a halt. But using this little drive here, it's able to compute that in, 95 milliseconds, which is quite impressive. So cool, it knows it's a cat, but let's try something else. Okay, we've got gang member here. Let's do that one. Right. So in this case, 29.4% Egyptian cat, 14.1 tabby cat, 2.9% plastic bag. Right. So you can see it is pretty accurate with your typical objects if we're working with cats or gangster cats. Let's do Sydney since we're in Sydney. Right. So in this case, 88.1% steel arch bridge, pier, 5.9%. It's pretty accurate. Google's image set. So you wouldn't really want to train this yourself unless, so what you could do is you could use Google's predefined neural net architecture and give it your own images, and it will give you similar accuracy if you have enough images. So if perhaps you're working in the agriculture space, in one of our projects we had pest control. So in agriculture, when you're growing plants, some pests are actually good for certain plants and some are terrible for certain plants. Given enough images, what you could do is perhaps train this network to figure out what the specific pest is and make decisions based on that, if you have these sensors available on a farm. Right, so I urge you to try it out now that you have a basic understanding of how neural nets operate under the hood. Explore it further. There's tons of resources online. If you're interested in courses, Fast AI, they have a really good blogs and free courses, online courses. If you're really interested in the math behind it, the founder of Coursera, Andrew Ng, he's got an excellent course on deep learning, which really dives into the mathematical theory if you're interested in that side of things. Experiment with your projects. Figure out what data you have, how you can use that data, and maybe through that you'll really build something awesome going forward. Thanks.
Just wanted to ask a question. Could you share with us why did you choose an S-curve for your activation function? Was it some principle or something that you were using?
Okay, so the question is, why did I choose the S-curve? So the sigmoid function.
Yes. Why did you do that? Was there any principle? Why that for an activation function?
So
It's kind of complicated if you don't get your activation function right.
yeah, so the sigmoid function is a common function that's used, and it's typically used if you want to find a probability. So when we use the step function, we wanted to find an absolute, 0 or 1. In that case, we wanted to find a probability. What's the chances that this would be likely? And given that our data was scaled between values between 0 and 1, the sigmoid function made sense. Cool, thanks everyone.